In this topic we'll be looking at the structure of substances, by which we mean how the atoms or ions are arranged. We'll explore the links between structure and the type of bonding a substance has, and we'll see that the bonding and structure in turn determine what the properties of a substance will be, whether it will be brittle, or whether we can bend it into different shapes, or whether it will take lots of heat energy to melt it, or whether it will have already melted and boiled at room temperature and be found as a gas, and so on. We'll start by looking at substances which have ionic bonding. The structure of every solid substance with ionic bonding is the same. If we could look inside the solid, we'd see a regular repeating three-dimensional pattern with alternating positive and negative ions in every direction, which we call a giant ionic lattice. Throughout the lattice, the oppositely charged ions are adjacent to each other, so in every direction there are strong ionic bonds locking the ions into place in the lattice. The bonds are strong because they arise from the electrostatic attraction between the ions, which of course are oppositely charged. You may be asked to draw a giant ionic lattice like this one for sodium chloride. Don't panic, you're not being asked for a work of art. Just remember to draw alternating positive and negative ions in each direction, and then build up your diagram in layers. The strong ionic bonding and three-dimensional arrangement lead to substances with giant ionic lattices having characteristic properties. We can recognise a giant ionic structure because it will have high melting and boiling points. It will be crystalline and brittle, and although it won't conduct electricity when it's solid, it will conduct electricity if we melt it, or if we can dissolve it in water and make a solution. We need to be able to explain why a giant ionic lattice would have each of these properties. The high melting point is easy to explain. When we melt the solid substance, we have to break the strong ionic bonds between the ions so that the ions are free to move around in the liquid state. This takes a lot of energy, so a high temperature is required. The explanation for high boiling point is similar. The strong attractions between the oppositely charged ions in the liquid have to be overcome to form a gas, where each ion is separated from all the others. We can see that there is a pattern to the melting points of ionic substances. If we look at the individual ions, we find that the melting point increases with the charge on the ions. The larger the charges on the ions are, the stronger the electrostatic attractions are, and hence the more energy that will be required to break the ionic bonds and melt the substance. Here, for example, we see that the 1 plus and 1 minus charges of sodium chloride lead to a lower melting point than the 2 plus and 2 minus charges of the ions in magnesium oxide. The regular repeating pattern of the ions means that giant ionic lattices are crystalline when they're solid. The shapes of the crystals reflect the arrangement of the ions at the atomic level. The crystals are brittle. It's easy to see why. If a stress is applied to the crystal so that one layer of ions is forced to move, then ions of the same charge end up next to one another, and like charges will repel, so the two parts of the crystal will be literally pushed apart from inside. To understand solubility, we need to understand a little about the process of dissolving. There's a lot more to this than we're covering here, and at A level you'll look at the enthalpy and entropy changes which determine whether a substance will dissolve and the temperature change that will take place when it does. Put simply, to dissolve a giant ionic structure, the water molecules have to overcome the ionic bonds which hold the substance together, then the water molecules have to surround the individual ions in the solution, forming bonds with them, which releases energy. If the ionic bonds are very strong, which happens when the charges on the ions are larger, for example in magnesium oxide, then the water molecules can't break the ionic bonds in the lattice. In a similar way, solvents other than water, for example petrol, can't form bonds with the individual ions and so can't dissolve giant ionic lattices. The ability to conduct electricity is all about charge carriers. Charge carriers, as the name suggests, are charged particles which are able to move and carry the electrical charge. Remember, an electric current is the flow of charge. In a giant ionic lattice we have charged particles, the ions. but they're locked in place in the lattice and unable to move, so the charge can't flow. Once we melt the lattice or dissolve it into a solution, however, the ions are now free to move, so they can carry the electrical current throughout the solution as they flow. By way of contrast, let's take a look at simple molecular substances. A large number of everyday substances in our world are simple molecules. The gases in air, oils, water, and even the chlorine we dissolve in water to kill any microorganisms. Inside a simple molecule, the atoms are held together by strong covalent bonds. Between the molecules, there are much weaker forces holding the molecules to one another. We call these weak intermolecular forces. It is because these forces are weak that most simple molecular substances are gases or liquids at room temperature. We can identify a substance with simple molecular structure easily. It's the only type of structure that has a low melting and boiling point. Simple molecular structures do not conduct electricity even when liquid. The reason why simple molecules do not conduct electricity is simple: no charge carriers. There are no ions that can carry the charge, as simple molecules have covalent bonding, and all the electrons are either held by individual atoms or forming covalent bonds. Nothing charged is able to flow to carry the current. To understand the low melting and boiling point, we need to appreciate that to melt or boil a simple molecular substance, we don't have to break any bonds. This might be surprising, but think about ice. Ice is still water, just with the water molecules locked into place as a solid. Ice is H2O in the solid state. When enough of the weak intermolecular forces that lock the water molecules together in the ice have been overcome, clumps of water molecules can move around. This is H2O in the liquid state. It's still H2O. No bonds have been broken. When the last of the weak intermolecular forces have been overcome and the individual water molecules are separate from one another and move around independently, we have steam, H2O in the gaseous state. Still no bonds broken, only weak intermolecular forces overcome. And hence, this only takes a little bit of energy. The difference between the large amounts of energy needed to break the strong ionic bonds in a giant ionic lattice and the small amounts of energy needed to overcome the weak intermolecular forces in simple molecules is clearly shown in the differences between their melting and boiling points. Substances with giant covalent lattices have more in common with giant ionic lattices than with covalently bonded simple molecules. It's the strength of the bonds throughout the lattice rather than the fact that the bonds are covalent which is important. Well-known substances with giant covalent structures include quartz, which is silicon dioxide, and diamond and graphite, which are both forms of carbon. You may notice that silicon and carbon are both group 4 elements, and it's the fact that these elements have a valency of 4 that allows them to form bonds in enough different directions to form a three-dimensional lattice. We can recognise a substance with a giant covalent structure because it will have the high melting and boiling point characteristic of a giant 3D lattice, but it will not conduct electricity when solid or when liquid, which is characteristic of covalently bonded atoms. The strong covalent bonds throughout the lattice take a lot of energy to break. This explains the high strength and the high melting and boiling point of substances such as diamond or quartz. It also explains why they are unreactive. The strong bonding means a high activation energy for any reaction involving giant covalent substances as reactants. The lack of electrical conductivity is due to a lack of charge carriers. There are no ions, and all the electrons are either held by individual atoms or used in covalent bonds. The exception is graphite, a giant covalent structure which does conduct electricity when solid, a characteristic normally associated only with metallic structures. We'll look in more detail at graphite later, but first a little more about diamonds. The structure of diamond shows that inside the lattice every carbon atom has 4 covalent bonds, each to another different carbon atom. This gives rise to a structure with tetrahedral shape at each carbon atom. Drawing the structure of diamond isn't too difficult if you practice drawing a single carbon atom with 4 bonds in a tetrahedral arrangement, like the one at the top of the diagram here. Now draw the same thing downwards from the carbon atom on the left, and again the same thing joining the 2 carbon atoms coming forward to the left, and again down from the original carbon atom on the right, joining to the rightmost carbon atoms of the 2 tetrahedral carbons you've drawn underneath. The strength and high melting point of diamond make it an excellent material for cutting tools and drill bits. Industrial diamonds are widely used for this purpose. Turning our attention to graphite, which, like diamond, is entirely carbon atoms, we see a very different arrangement. The carbon atoms are in layers, each layer comprising interlocking hexagons. Each carbon atom is bonded to 3 others with strong covalent bonds in a planar triangle, so each carbon is only using 3 of its 4 outer shell electrons for bonding. Between the layers, however, there are only weak forces holding the layers together. This arrangement leads to some unusual properties. Graphite has a high melting and boiling point because it takes a lot of energy to break the strong covalent bonds within each layer. It's a soft material, however, because the layers can easily slide over each other as the weak forces are overcome. The electron in each carbon atom's outer shell that's not shared in covalent bonds becomes delocalized. This means it's not held by the atom, but free to move throughout the structure. An electron is a negatively charged particle, so these delocalized electrons can act as charge carriers, flowing throughout the structure to carry an electric current. Because of the ability of the layers in graphite to slide over each other, graphite finds use as a lubricant. Pencil leads are made of graphite because as the pencil tip moves over the paper, a trail of graphite layers is left behind on the page, leaving a clear mark where the pencil has been. The high melting point and conductivity, coupled with the lubricating property, make graphite useful for moving electrical parts, such as the contacts in motors. Finally, we'll look at the giant metallic structure, formed by substances with metallic bonding. Recall that metal ions are bonded in layers, with the delocalized electrons from the outer shell surrounding the ions in the layers and able to move throughout the structure. Remember also that metallic bonds are strong, arising from the electrostatic attractions between the metal ions and the delocalized electrons. The typical properties of metals are explained by this structure: the high melting and boiling points, their ability to be bent into shapes and drawn out into wires, that's being malleable and ductile respectively, and their ability to conduct heat and electricity effectively when both solid or liquid. The high melting and boiling points are easy to explain. Metallic bonding is strong, so lots of heat energy is required to overcome the metallic bonds throughout the giant metallic structure. We can also see that as the valency of the metal increases, it will have stronger metallic bonds and a higher melting point. This is because each metal ion has a higher charge and has donated more electrons into the sea of delocalized electrons surrounding the metal ions and locking them into place. The delocalized electrons are charge carriers and so result in metals being good electrical conductors, but they also spread vibrational energy throughout the metal structure as they move, and so make metals good conductors of heat. The arrangement of metal ions in layers which can slide over each other means that metals can be shaped, bent, or drawn out. As the layers of metal ions move over each other, the delocalized electrons move too between the layers, keeping them bonded together, so metals are not brittle in the way that crystals of a giant ionic lattice are. Nonetheless, metals do have a crystalline structure. It's not easy to see normally, but the crystals on the surface of a metal object that has been galvanized by coating it with zinc are easy to see in the way light reflects off the metal surface. These metal crystals, in which the layers are all aligned, are called grains. In adjacent grains, the layers will all be aligned in different directions. Between the crystals are grain boundaries. Heating and cooling regimes can change the grain size and grain boundaries, allowing some properties of metals, such as hardness, to be modified. Strictly speaking, only elements can be metals. As soon as there's more than one type of atom present in a giant metallic structure, it is properly called an alloy. Because atoms are different sizes, adding a small amount of a differently sized atom to a metal has a significant effect. The layers are disrupted and no longer able to slide over one another. While pure metals are soft, alloys are significantly stronger, making alloys much more useful for structural purposes. For example, aluminium is one of the lightest metals, but too soft for making aircraft bodies. Aluminium alloys are tougher and therefore perfect. Steel is another example of an alloy. Different elements mixed in small quantities into iron create different types of steel. For example, iron is alloyed with chromium to form stainless steel. Other alloys, such as brass, solder, and the mercury amalgam used to fill teeth, are commonly used. Gold too is usually an alloy. Our gold jewellery would be too soft for practical use if made from pure 24-carat gold, so alloys with copper, silver, platinum or palladium produce more hard-wearing and also different coloured gold items. More recently, scientists have been creating alloys which are capable of sensing and changing in response to conditions such as temperature. Smart alloys are capable of being formed into a shape which is then locked into a kind of structural memory. The metals can be bent or deformed, but when heated above a certain temperature, the metal bends itself back into its original remembered shape. This has a variety of practical applications, for example in dental braces, which can be bent to fit around displaced teeth, and then when warmed to the natural temperature of the mouth will bend back into their remembered shape, moving the teeth slowly back into place, but with no pull on the teeth once they are in the correct place.